Hi, in this video we are going to discuss tail events. You may remember when we were talking about Borel-Cantelli, I mentioned that there are some events which can only happen with probability 0 or 1. So we are about to meet those events now. I will start with a definition which is not quite straightforward, so bear with me. I will write it down and then I'll try to explain everything. So I'll start by saying that I have a sequence of random variables. I'm not making any assumptions about it, like independence or something, no assumptions yet. And then for any n, I define the sigma algebra tau n as simply the sigma algebra generated by the random variables xn plus 1, xn plus 2, and so on. And this sigma algebra is called the nth tail sigma algebra of xn. What is happening here is the following. If we draw our usual picture with omega, r, and a bunch of mappings between them, then first of all, this definition tells us, well, ignore x1 up to xn, only look at xn plus 1, xn plus 2, and so on. And secondly, it tells us take the Borel sigma algebra, so the sets in R, Borel sets in R, and take their pre-images under each of those random variables. So for xn plus 1 will give us some pre-images which I mark red. Xn plus 2 will give us some pre-images which I mark green. Some of them can be the same as the red ones, some will be different. And I get a different color for every next random variable. So this gives me a bunch of sigma algebras, and I mix them all together. So I take the union of those sigma algebras. Unfortunately, this is not immediately a sigma algebra, because the union of sigma algebras is not a sigma algebra per se. And therefore, I take the smallest sigma algebra generated by the union of all those sigma algebras. And this is what tau n is. Okay, so now if we understand tau n, we also understand that they are getting smaller and smaller and smaller, right? Because when n grows, I'm throwing in fewer and fewer sigma algebras. So this means if I want somehow to pass to the limit as n goes to infinity, it makes sense to take the intersection of tau n over n from 1 to infinity. So this is a sigma algebra because a countable intersection of sigma algebras is a sigma algebra. And this sigma algebra is called the tail sigma algebra. Of xn. Now, it would be good to see some examples, but before we look at the examples, let me try to explain the intuition behind those definitions. And to do so, I need to go back a little bit and actually just talk about a single random variable. So if I have just one random variable, then if I look at its sigma algebra, then we know it's just the collection of all sets of this form, right? And it means it's exactly the sets about the occurrence or non-occurrence of which I can judge if I know the value of my random variable x. So like if B, for example, is the interval 0, 1, and I evaluated my random variable x, I got the value 5, then I know this event doesn't occur. And if the value was 1/2, then I can say the event occurs. So whatever value of x, whatever random value of x, once I know the value, I know whether the event occurs or it doesn't. Now, how can we interpret? So in a way, sigma algebra of x is the information which we can get from the random variable x, right? So in particular, tau n is the information which we can get from all random variables starting from number n plus 1. And this means that informally, I can describe tau n as the collection of events which are defined by random variables xn plus 1, xn plus 2, and so on only. So, for example, if I look at the event, let's say x5 belongs to 0, 1, x10 is less than 20, and then maybe xn is positive for all n greater or equal than 20, then this event, it belongs to tau 4, right? Because it is determined by the random variables numbered 5 and higher. And then obviously it belongs to tau 3 and so on up to tau 0, because those sigma algebras are contained in each other. But it doesn't belong to tau 5 because tau 5 only contains information about x6 and higher, and here I'm required to check whether x5 satisfies something, and tau 5 contains no information about x5. Okay, so now I can actually rephrase it slightly, and this new this new sentence will actually give us an even better idea of what's going on, and say that those are events that do not depend on the initial n random variables x1, xn. Events that don't depend on x1, xn. Okay, but now we come to an interesting question. What is then the description of tau? If tau n is the sigma algebra where events don't depend on the initial n random variables, what is tau? I mean, when we take the union, it means can we like drop all random variables, but that doesn't make any sense, right? So maybe pause this video and think what the answer could be, because this question is really interesting and the answer is not too difficult. And now I tell you what it is. So tau contains events which do not depend on any finite number of random variables xn. So events that don't depend on any finite number of xn. And if we try to state it in terms of the tail of the sequence, so to say, so the random variables which stay in the sigma algebra similarly to this line, we can say that tau contains events which are determined by the tail of xn. This means that, well, this means exactly the same as the red line. So I can drop any finite number of my random variables, and the tail, which means whatever is left of the sequence, will still tell me whether my event is occurring or not. Now we do need some examples to see this all working. So the first one is that, so the event E, that xn converges to some number a. Xn converges to some number a. Now, if we think about it, whether or not a sequence converges to a doesn't depend on its first term, doesn't depend on its second term, actually doesn't depend on any first m terms, right? So it feels like it is a tail event, and let's prove it formally. So intuitively, I think we all agree that it is a tail event, but what would the formal proof look like? So we want to prove that it belongs to Tor, and remember that Tor is the union over all m of Tor m. So this means I need to show that E belongs to each of Tor m. So this means I fix an m, and I'm going to say, well, this event is the same as the event when the sequence shifted by m, so m plus n converges to a, right? So it's simply that the m plus 1 term of my sequence becomes the first term, the term m plus 2 becomes the second term, the term m plus 3 becomes the third term, but it's still this. So the convergence either occur for both sequences or for neither. And then you see, I somehow removed the first m terms from the definition, but to be even more precise, I'm now going to write down the definition of this convergence, which is for every k, there is a capital N, such that for all n greater or equal than capital N, mod x m plus n minus a is less than 1 over k. Now, here I can see explicitly that this event belongs to Tor m because it is determined by a random variable with index larger than m, right? And then I'm taking some unions, I'm taking some intersections, I'm taking again some unions, but if I'm doing so with the sets from Tor n to m, then I get a set from Tor m. So this means this whole set belongs to Tor m, right? And this means we have formally proved that our event is a tail event. Now I'm going to write down several examples, and for each of them I want you to think whether it is a tail event or not while I'm writing or pausing the video after I finish writing. So the first event is going to be the limit of xn exists. The third event will be the series xn converges. The fourth event will be the series does not only converge, but its sum is positive. 5, the limit of the averages x1 plus xn over n exists, and the last one, the supremum over all n, over all n from natural numbers of xn is positive. Okay, so you can either pause the video now or just hear from me what the answers are. Okay, so let's look at this one. Here the idea is very, very similar to part one. Whether or not the limit exists doesn't depend on on any finitely many initial terms of the sequence. So this event belongs to Tom. Now, whether a series converges or it doesn't is not influenced by the behavior of the first few terms. So very similarly, we can say that this is a tail event. However, if we look now at part 4, we don't only want convergence, we want the sum to have a certain property. And the sum is influenced by any terms, right? Maybe I have a huge term, number 1, right, which pushes everything to the positive. So this event is not a tail event. Although I haven't proved it. So we only discuss the intuition now. Now, this example number 5, this is when I regret that I have to record the videos rather than having a live lecture, because this is where the audience usually splits into two halves. Because clearly we have all random variables from 1 to n in the description of our event. So this feels like they are important, and it feels like it can't be a tail event. But if you think carefully about it, you will notice that x1 plus xn over n for every m can be written as the sum of the first m terms divided by n plus the sum of all remaining terms from m plus 1 to n divided by n. And since m is finite and n is going to infinity, we see that this term goes to 0. So this means convergence of this term is equivalent to convergence of this term, and this term doesn't have x1 up to xm in its description, which means the first m terms are not influencing occurrence of this event. And this means it is a tail event, because this was true for every m. And finally, this event is not a tail event because the supremum, in a way, can happen anywhere. So if I have a large value for n equal to 1, then maybe this will be where the supremum will be taking place, and therefore all the terms are important. So this is not in Tor. I suggest we now prove something. So we proved carefully in the example 1 that the event E is a tail event. So I suggest now we do one of the cases where the answer is negative, so either 4 or 6, where the event turns out to be not to be a tail event. So let's do 6. Let me erase everything except the question which we want to do. Okay, so I suggest we construct a counterexample to the statement that it is a tail event. So to be precise with this statement, it can be a tail event for some particular cases. When, for example, all random variables are equal to 0, because the tail sigma algebra will be the degenerated sigma algebra consisting of the empty set and omega only, and so is the sigma algebra of every random variable. So it might be a tail event, but our question is a general question. Is it always a tail event? And here the answer is no. And therefore it's enough to come up with an example showing that it is not a tail event in that example. And my example will be as follows. I will define x1 as a random variable such that it takes two values, 2 with probability 1/2 and 0 with probability 1/2 also. And all other random variables will simply be 0 for all n greater or equal than 2. Then this event, let me call it E, so this event E is the same as the event x1 equals 2, right? Because when is the supremum strictly positive? Well, all those random variables can't be strictly positive. It can only happen when x1 is equal to 2. So this means the probability of it is 1/2. And what is important here is the following. So we managed to write this event E in this form, and it is tempting to say, oh, look, it does depend on x1. But we know from example 5 on the previous slide that it can be misleading. Maybe this dependence is not actually there. So we need to do a little bit more to show that E cannot belong to the tail sigma algebra. So this is why I'm continuing and saying that the probability of E is 1/2. But on the other hand, let me find the tail sigma algebra tau explicitly. So tau2, or more precisely tau n for any n greater or equal than 2, is the trivial sigma algebra consisting of the empty set and omega, because those random variables are deterministic. And in part, so this is for all n greater or equal than 2. So since tau is the union of those, tau is also the trivial sigma algebra. So you see, there is no need for me to talk about tau1, because I'm going to intersect everything with the trivial sigma algebra anyway, and I will end up with the trivial sigma algebra anyway. So this is my tau, and it has two sets only. The probability of the empty set must be 0. The probability of the set omega must be 1. And this means neither of them can be my set E, because I know for sure that the probability of my set E is 1/2. And this is a formal proof that the set E is not in the tail sigma algebra at all.